Hey, what's up, Mike?
How you doing, man? Good morning, man.
Good morning.
Hey, I wanted to ask you when you're doing the JK flip flops and all those problems that have that, um, how do I know what to put for clear and what to put for start?
For set and clear,
Yeah, yeah. I apologize for set and clear.
um, well, it depends on the problem. If they ask you to use it somehow, if the question somehow is related to clearing the count or something, then that's when you know you use it. Otherwise, you can just ground them on or put VCC depending on the activation level.
Yeah, if it has a bubble on clear, the best bet is to put a VCC, right?
Yeah, if you're not gonna use it because that's you're disabling.
And what I did for one of the problems, start, I connected it to set since it was low and it has a bubble.
Um, Well, but it depends, right? Because start hey Irvin,
Hey, what's up?
start uh um it wants you to clear the count, right? So if you put it to set, when you set in the JK flip-flop, you're setting it to 1. You see what I'm saying? So if the initial count it's 0 0, you wanna, for instance, connect the start input to all the clears in your flip-flops,
Oh,
right?
okay.
So you will clear all of them and the count will be 0 0. So
Or or
if by
whatever
any,
count they give you, right?
yeah, so if it's another count, for instance, 0 1 0, then you will connect the start to the clear of two of the flip-flops and then to the set of one of them.
Okay. Yeah, no, and so when would I want to connect anything to set?
If the count is, for instance, a 1, if the count they want is a 1, then you will connect it to set. The most important thing is that you don't understand that what set does is it sets the output to 1 no matter what J or K are. And it's the same thing with clear. They do not take into consideration the J and the K input. They immediately the output becomes a 1 or a 0 depending if you're setting true set or clear. And there are two types of ways you can do this. You can do this asynchronously or synchronously. Asynchronous means immediately the output is going to be whatever if you set it or clear. And unsynchronous means that it's going to wait for a clock edge and then it's going to set the output to whatever you set it. Do you understand?
A little bit more, yeah.
But so when it's asynchronously, you just use set and reset. But when it's synchronously, you have to consider your start variable into your K maps, right? And get an equation for that.
Yep, exactly.
Yeah,
Yeah.
because you cannot connect anymore to set and reset because if you connect to set and reset, it will be like instantaneously. At the moment that set goes on, it will change it. But that's not the way we want it. We want it synchronous, right?
Well, not exactly. Um,
Yeah, if we want a variable start to be synchronously, which means we need to wait for the next rising edge of the clock or whatever, we have to consider our start into our truth table, right? And draw there when it's gonna become 0 and when it's gonna become 1. Like in the lab, I don't know if you all TAs do the same lab quiz or not for lab
not really.
5.
Okay, so what happened?
She gave us a counting sequence and then she gave us a start which was synchronous, and this start, every time the start goes on, the variable was pretty much locked, like the output was locked into one variable, 0 1. And uh and uh we had to treat it, we had to, like, she shared 1 second, I can I can share the tab for that. Because she shared it with us. Alright, I'm sharing screens.
Okay.
Hey, Reynaldo, I can't see. Oh no, no, I see this now.
So yeah, she has here,
Oh, that's Divia's, huh?
yeah, that's the one we had a quiz.
Yeah.
That's the one we had a quiz. So she has this sequence, and then she wants as a start to be at 0, 1. So she has to treat and has to be synchronous. And has to be synchronous. So we treat start as a variable, right? Every time start is 1, the variable is locked. The next state is locked at 0, 1, 0, 1, 0, 1, 0, 1. But when the start changes to 0, we keep counting. So the next state is gonna be different.
I think you're a bit confused, Irvis. The synchronous and asynchronous doesn't have to do with if with that. If it's not such an easy state you're returning to, such as 0, 0, then you do have to do a K-map and a function for your start and your sets and clears. But the fact that it's synchronous and asynchronous doesn't have anything to do with that. The only thing that changes is what I told you is the timing.
Okay.
Um,
But let's say we were supposed to use a synchronous start. We cannot connect um, connect start to the first set and the second clear, can we?
yeah.
But it's synchronous, and at the time that the start will go on, it will change automatically, right there. We want it to be synchronous, not asynchronous.
Okay, so what happens is it's some parts, right? Like some ICs, they have asynchronous resets and clears, and some others don't. So you can control that. You cannot make a chip that had an asynchronous set and reset all of a sudden be synchronous. You see what I'm saying? You'll have to use another chip, and that will have the set and clear synchronous. Do you understand what I'm saying? It's not like you can add some parts and make it synchronous. You'll have to use a different chip that will have a synchronous set and reset, set and clear.
Okay. So he has to specify that whether the set and clear are synchronous or asynchronous.
Yes, exactly. That's what I'm trying to tell you. It's not you cannot make it synchronous. He has to tell you like in the exam, one of the exams we were looking at yesterday, like he tells you like the set is asynchronous and the clear is synchronous. That's
Okay.
specific for that chip. You can't change that.
Okay. All right. And another question, since we're talking to the to this sets and clears and all of them. Um, remember we were doing um, we were doing this problem yesterday.
Yes, that's exactly the one I was talking to you about.
Yeah. Now I understand when it goes high, when it goes like if I don't know what was it here. So here it was a synchronous clear and a synchronous set. So I understand that when it's synchronous, he has to wait for the clock, and when it's not, it doesn't wait for the clock. But what happens when you go at the end of the input? Like let's see the set right here.
Mm-hmm.
The set is synchronous, so the set goes here, goes on,
Mm-hmm.
or whatever, but it has to wait for the clock, which is right here, and
Mm-hmm.
then it will set it to 1, the output, so Q1 will go to 1. But
Mm-hmm.
so between here and here, when the set goes back again to off, what happens? Nothing, or it just waits for the next clock?
Yeah, it's nothing. It's just like if it was a JK input, nothing happens. It goes, the only times you're looking at the at that set, it's on the clock edges. So right immediately when it goes off, that's it. It's only at the next clock edge when it matters.
Okay, so when it goes back off again, you don't care about that. You just keep going then, right?
Yeah, you just keep going.
Same here with the reset. I know that reset is asynchronous, so the reset goes on here, which means immediately the queue goes 0. But then
Hmm.
when it goes off again, you don't really do anything. You just wait for the next clock, right?
No, that is different. That is well, yeah, yeah,
Well, yeah,
because the next clock edge is when you're gonna look at J and K again. So basically, yeah.
so when the set and reset go off, like here or here, you don't really take that. You don't do anything there. You just wait for the next clock or the next set or whatever thing will happen, right?
Mm-hmm. Yeah,
Okay. All right.
Let me ask you a question. J, J and K don't have activation levels, right?
they could have.
They could have.
They all the inputs and outputs have activation levels. What is the J and K current activation levels in that problem?
Yeah,
Do you
no, it's
remember?
that high, but aren't those counters like it's not like isn't it always zero? Yeah, I didn't understand that. Like, how could it be like a low J? Maybe the input that's going in could be, but I'm saying like the JK itself.
Yeah, like remember, truth tables and excitation tables don't have activation levels. The things that have activation levels is the chips and quarters and stuff like that. But when you're doing your truth table and activation levels, you don't take that into account. You only take it into account when you're doing your voltage tables and when you're looking at the chip.
For these problems, did you do a voltage table, Irvis?
For the number 5 that we're talking earlier, for those ones.
Yeah, because I for this test I didn't do any voltage tables for the flip-flops.
No, I didn't do those voltage table because and I kind of started and then halfway kind of stopped, but and I was trying to run it on. Well, for the first one, I did some voltage table because I created on paper and then I was trying to check it on Cordus, so I simulated on Cordus, and Cordus, of course, knows only voltage table, so I had to make a voltage table to check it whether I was being right or wrong. But you have to take again, all you need to know is that when the input or output is low, your 0 becomes a high and your 1 becomes a low, and when it's high, your 0 is a low and your 1 is a high. That's all you need to remember, and then you can sort that out in increasing order or decreasing order.
All right.
Hey Ronaldo, what's the difference between an SR flip-flop and a JK flip-flop?
Can you tell me?
I don't know, cause I was working the same quiz that I showed you earlier, and I was working in all the different ways with all the other flip-flops and see the thing, but I never, like, when I was working with JK, I got the same equation, and with the SR, I got the same equation. Now, I know that in an SR, you don't have the toggle option, so when it goes from 1 to 1, it does nothing, like, it's like it's like a don't care. And an SR, I know that, but I just don't know why, when you create a counter, why would you use a JK flip-flop and an SR flip-flop?
Well, he's gonna tell you specifically what kind of flip-flops he wants you to use, but basically the main difference is that you mentioned that the SR has, well, and also the equations are different, right? So those are the two big difference, the equations and that the SR you cannot have both being true. So you have to take that into consideration. You see what I'm saying?
Okay. All right. Um.
When it asks you to use an only open collector gates of any real SSI type, like this problem right here, that's the one that has a little line after, right?
Yeah.
So I'm gonna do this really quick, this problem, and okay, use
Have there in any exams been like shifters and state machines and all those? Because I've been
Oh.
going through pretty much all the exams and I haven't seen any like shifter or adder or something like that.
I will go by the practice exams, but basically everything is fair game. You know, it's kind of unlikely, but he can always throw it because he went over it. You see what I'm saying?
Yeah.
Everything that he has covered so far on these slides is basically fair game, you know, but
All right. Okay. I know we touched it yesterday a little bit, but I didn't really understand. There was on 10. It was 10 on summer. Yeah. It was 10 on summer 2012 with the tri-stated muxes and that you kind of explained a little bit, but I didn't understand what the tri-stated in the mux do and what doesn't it do. Can we go over that one time?
mm-hmm.
So it's number 10 on summer 2012.
is this how you do this?
Yeah, that looks about right.
And I connected to VCC always at the top, right?
Mm-hmm.
And if G was, let's say G was active low, then I will have to put an inverter there before it, right?
Yep.
All right.
So Ronaldo, did you open that number 10?
On it. What test was it again?
Summer 2012.
Okay.
Um, you can see my. No, you cannot see. Hold on. I'm gonna share what I did. Right, so you can see my screen. So for number one, he just wants you to create a, s- a f- a 6 input mux or like a 6 input mux with no enables, right?
Mm-hmm.
So 6 input will be 2 will be the select line and 4 will be the inputs, right? So
Right.
4 plus 2 will be 6. Now at part B he says to create those to
No,
create
no, 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 no. Wait. No,
What?
no, no. Six input means you can choose six things.
Oh, so
That's
you
what it
need three
means.
select lines.
Yes. So with the parts you have, you need to build a six input mux.
So on part A, I need to add a C in here and add a S2.
Well, do you have that part in the ones he's giving you?
Well, no, he's like, if you read part A, he just says, draw a functional block diagram of six input muxes with no enables. With input
Oh,
should
okay.
be, so like, he just said draw it.
Okay.
So you just draw it like this, like I'm drawing on paint.
Yeah, yeah. Yeah,
Alright,
that's good. But remember to add the other two inputs.
so
You're gonna
C,
have C5 and C6.
okay. Alright. Now in part B, he says to create the same thing, but using tri-state with no enable, but using this tri-state enablers and no tri-stated, and I don't know much. So can you connect this y1 and y2 together?
Well, that's what the tri-state means, right? So when you have a mux that's tri-stated, what it basically means is that you can connect its output to another tri-stated output.
Okay, but
So
do both of the muxes need to be tri-stated or just one?
both of them.
Okay, so so I have a one mux which is a 4 to 2.
Give me 1 second, sorry. You give me just one quick second.
Okay.
Go ahead.
So I have one mux here which is a 4 to 2, and I have another mux which is a 2 to 1. And then I have the enabler which I selected, the tri-state enabler with select lines and then this is the other tri-stated. And then I have y1 and y2, and this will be good. This will be a 6 input mux.
Well, he's telling you that both with no enable, right?
Yeah,
So this all of these muxes they don't have enables, right? So you can basically forget about the enable.
but the enables, but the muxes have to have tri-stated or not tri-stated enables.
Let me read the question. Just give me 1 second.
Yeah, it says no enables using only four input, and then it says with tri-state or non-tri-state enables. Well, couldn't you just use the non-tri-state and then connect the enables?
Well, the only way you can connect the enables if they is by using the tri-stated ones, right? So you will need to connect um either you can choose either S0 or S2 and make that your enable, right? So you can that's when you can choose just one select line and make that your enable. But if you have the non-tri-stated ones, then it gets complicated. So do you guys see it or you want me to keep going over it?
I'll say if you can keep going it, because I don't really understand how you can use the non-tri-stated or tri-stated enablers to.
All right, so let's do the whole thing, right? So hold on, give me 1 second. you guys see my screen?
Yeah.
Right, so what we need to build, it's a 6. Right, so here we have one input. These are the inputs. Right, and these are the select lines. And then we have one output. And then we
Yeah.
need to build this with these parts.
Okay.
Alright, so then if we want the minimum solution, um,
He's asking for two solutions there.
okay. Okay, so let's do one. So for one, we're gonna use the 4 input tri-stated mux and the 2 input tri-stated mux. And what's tri-stated is the enables, right?
Okay.
So then this will be uh, the 4 to 1 with the enable tri-stated, right? So
Yeah.
select lines will be S0 and S1. And then we have an enable here that we need to do something about it, right? And let's do
Okay.
it for now. So, and then we have
This is office hours
the 2 to 1.
for TA. Yeah.
So here we're gonna connect
Yeah.
the other two, and we're gonna give it this other
I'm waiting for someone to
these two
reply.
select.
All right.
I have no idea. It's not my fault.
So you connected the tri-state enable to the 2 to 1 mode.
Right. Right, and then we have one output, right? So then the enables, for this enable, you guys can see it's kind of like, do you guys understand what I've done so far?
Yeah.
You have an enable only on the 2 to 1 mux, right? Which is a select line for that one.
There's an enable on both of them.
And both the enablers are tri-stated, right?
Yes, I'm using the tri-stated one.
All right. Yeah, I understand what you've done so far, but I don't know what you're gonna do with the enablers.
Where do you have the other enable connected on the 1, 2, 3, 4, 5? I don't see the other enable.
Well, the 4, I haven't connected any. This is the 4,
He
right?
hasn't put the enablers yet.
This is the 2, and this is S2, S1, and S0, right? So I haven't connected the enables yet, right? So
Yeah.
then the thing is that these two outputs, you see, this is where I'm confused about, because if the only thing that's tri-stated is the enables, then you can never connect the outputs together. So you will need another mux here to select between these two. Between which output, because you can't connect the outputs together. As far as the enables, what you could do, you don't really need to, honestly, you don't really need them to be tri-stated, because you could use, for this guy enable, he's only gonna be enabled when S2 is a 0 or a 1. And then we have to choose between these other two. Honestly, this is a question I'm not very sure about. I'll have to ask and get back to you guys.
All right. Yeah, that's what I don't understand. Like, what do the tri-state do, and or like I know what a tri-state does, but how'd you how'd you implement that? And he doesn't really have any examples that are clear about that or not.
Yeah, I'll have to get back at you guys with this.
Okay.
That question that I was doing with the open collectors.
Mm-hmm.
Okay, like on number one, that it's adding. That means I have to put an OR gate down here, right? Because it's adding.
Yes.
And okay, and down here I will put, instead of the OR gate, I'll put a AND gate or a NAND gate.
Yes.
So that's pretty much what it means then, right?
Yes.
Okay.
Hey Ronaldo, on the same exam, summer 2012.
Mm-hmm.
He has there is like a number 2B, and it's there are two inputs, A low, B high, in a quarters. How does quarters treat them, and what's the difference? Quarters doesn't treat them different, right?
Yeah, Quarters doesn't understand of any
Like
of that.
quarters would treat them the same way, right?
Yes.
Okay.
Ronaldo, I'm here doing number 6 there.
Summer 2012?
Yeah. Fall 2013, my apologies. And it's asking, determine the sequence of the outputs for Q1 high and Q0 high, starting at Q1 times Q1, Q0 equals 0, 0. And assume the asynchronous clear is false and a series of clocks occur to create the sequence of outputs show up. So all I got to do is go in order, right?
I'm sorry, can you say which question is that again?
6.
Question 6, hold on. Okay, so what's your question again?
Like, it's asking me to list the next 6 values in the sequence, but Okay, so I start at 0 0, and then I just go 0 1 1 0 1 1 0 0 and 0 1.
Is that summer 2012?
No, that's fall 2013.
Okay, hold on 1 second there. Sorry. Question 6.
Yeah.
Okay, so determine the sequence of outputs for Q1 and Q0 starting at Q1 0 0. Assume the asynchronous clear is false and a series of clocks occur to create the sequence outputs. So you will have to basically like reverse engineer this scanner, right, to figure out. So from here, you will have to get the truth table. There are a T and a JK, right? So from here, you will have to get the truth table, and from there, you will get the sequence, because it's a counter, right? But they're just giving you the counter is done.
Yeah, what I did was okay, I saw that J is equal to they connected it to VCC, so that J must be 1.
Right?
K
So the first thing is how many counts can you possibly have?
4.
4.
Okay. So then you know you're gonna have a, a 4 rows truth table, right?
Yeah.
So right there you can see there your J is gonna be all the time a 1. So you can already fill out that column in your truth table. And your K,
It's gonna be don't
it's
cares, right?
no, not really. It's gonna be equal to Q.
Not Q, right?
Um,
Not Q0. My apologies.
yeah, not Q0. So you can fill out, for instance, your initials like
Well,
your
like if
Q1 and
Q0 is 0,
Q0,
then K
0 0 0 1, and then your K is gonna be not Q0. So whatever you put for Q0, that's gonna be your K, right? And from there you can figure out what is gonna be your next states. Do you see it? The
yeah.
only one a little bit more complicated is the T, but you can do it. It's just Q1 ended with Q0, with not Q0. So you will have to do that, but it's not very difficult.
So okay. So when I'm looking at the next sequences for the J and K, okay, because I got the first 4 sequences. The next state, the sequence that and then to get the sequence for the JK, do I start from okay, like the Q1 plus I got it, and Q0 plus I got it to be after Q1 and Q0 0 0 0 1. How do I look at that? Do I go directly to the next column and then say my JK is 1 and 1? So that's gonna be the next state after Q1 plus and Q0 plus?
Yeah, exactly. So um, let me show you. So for instance, we're gonna have right your truth table, right? So you're gonna have in here I will put like Q0, Q1 and Q0. So in here you'll have your Q1 plus and your Q0 plus, and then you'll have your J, your K, and your toggle, right? So then you'll fill this up,
Yeah.
right? So we already determined that so here will be your 0, 0, 0, 1, 1, 0, 1, 1, right? So this will be your Q1 plus and your Q0 plus,
Hmm?
and this is your J, your K, and your toggle, right? So if you look, your J, it's 1 everywhere, so you
Yeah.
can already fill that up. So then your K is Q naught,
Yeah.
Q0 naught, right? So this is Q0. So then you'll have here a 1, here a 0, here a 1, and here a 0. Do you see why?
Yeah. I got that exact same thing.
Right, so now the only other one you have to deal with is your toggle, right? So
Yeah.
your toggle is equal to Q1,
Times
uh,
Q. So it's pretty much
and
Q1 times K.
yeah, exactly. There you go. So here's your Q1. You add that with your K. So here you will get a 0. Here you will get a 0. Here you will get a 1, and here you will get a 0. And that's it. You got it. So now you have to do, for instance, now you can get your Q1 and your Q1 plus and your Q zeros, right? Like going backwards from your J and K. So when the J and K is for which Q? It's for Q1, right? So when Q1 is 0 and your J and K are 1, 1, what does that mean?
That's what a toggle?
Exactly. So you just put a 1 here, right? So when your Q0 is 0 and your toggle is 0, what is your Q0 plus? What is your next state?
When your Q0 is 0 and your toggle is 0, that's a hold. It just stays, right?
Exactly. So it's just a 0. So then you keep doing this and you got right there, you got all your states. You see it?
Yeah, so okay, I keep on doing that until I get the next 6, right?
The next 4
Because
is
it's telling me 6. So it's just going to repeat himself.
yeah, it's just gonna repeat itself. Yeah.
All right. So, okay. 0, 0, 0.
So what I got is 10110101.
I didn't fill it up, but I'm guessing that's correct. I got 1-0 for the first one, so we got a 0 and your J is 1, so that's a 1. Your Q is 1 and your total is 0, so that's a 0. What else did you get? What you got? 1-0, 1-0?
Wait a second, why is that?
No, yeah, it's a 1. Your
Okay, it's a
Q0 is a
1.
1.
Okay.
So then you got a Q1 is 1, and you have J and K being 1, so you got a 0, 0, 1, 1, 1, 1, 1. So I got 1-0, 1-1, 0-1, 1-1. Is that what you got?
Why did you get a 1-1 at the end?
Your Q1 is 1, and your JK is 1-0.
1-0 is setting it to 1. Okay.
And then your Q0 is a 1, and your total is 0.
Alright, so it's 1011 10110111,
1-1. Mm-hmm.
and then it will go back again to
1-0.
So, okay, for the second number in Q1 plus, Q1 is 0 and JK is 1-0, and when JK is 1-0, it just sets it's 1, right?
Yep.
So you don't really even have to take into consideration the Q1, the number of the Q1. You just look at what JK is doing.
Well, you kind of, when it's just 1-0, you don't really need to take into consideration Q1. When it's 1-1, when your JK are 1-1, then you kind of need to, right?
Why? What happens when it's 1-1?
What happens when in your JK flip-flop when you have J being 1 and K being 1? What does it do?
It toggles, right?
Right? So how do you know what are you gonna toggle, right?
Oh, so the Q1 becomes a 0 then, right?
Right, you have to look at what's the current value, so the next value is going to be a toggle from that.
All right. All right. Q0. And for the T flip flop, when Q0 is 0 for the third column, I mean row, when Q0 is 0 and T is 1, that's a toggle, so it switches to what, 1?
Mm-hmm.
And it switches to 1 because the T's are 1, right?
Right.
So then, how come it switched to 1 on the last row when Q0 is 1 and T is 0? It toggles. Wouldn't it go to, or it goes to 1? Anytime it toggles, it goes to 1, right?
No, toggle, it's like an on and off switch, right? So if toggle is 0, you don't toggle, you just hold the value. So Q0 was 1, toggle is 0, I mean it's off. You're
Oh,
not going to toggle anything.
that's right. That's
So it
right.
just keeps its current value.
Yeah, when toggle, yeah, because the toggle is only when it's 1 when it toggles and it's 0 when it holds, right?
Right, so if you look at the first, like the very first Q0 one, Q0 is 0, your toggle is 0. So then your Q0 plus
It
is still a
holds.
0 because you're not toggling, you're just holding the value.
Hey, Ronaldo, on the same test, fall 2013, number 9.
Okay.
He has this muxes connected together and it says describe a function of the circuits below.
Um,
What question was that, Irvis?
Number 9 on 2013 fall.
And which one? A?
Yeah.
okay, so I think I'm beginning to understand. So when you have um, non-tri-stated enables, you can't connect the outputs together.
So in that case, we'll just say that a boom.
Yep.
Oh, because it's non-three state enable. Three states the same as tri-state, right?
Yeah, that's what he means. Tri-state.
So for the first one, we can just say that you cannot connect outputs together.
Mm-hmm.
Without tri-state enables, right?
Right. So
But
for part B, what would this be? Mm. Hello?
are they? Um, is the output active high? I'm assuming yes.
While one of them is active high and the other one is active low. Well, it doesn't have anything to do. So basically here, the thing that you can do is basically do this, right? With just one enable signal, right? So then
So
there,
one of them turns off whenever it's true.
right, and then
Not
there's always going to be one on. So what this is this is just a 6 input mux, right? This whole thing is just a 6 input mux.
Yeah.
So and the reason why you're able to do it is because of this tri-state,
Okay.
because the enables are tri-stated.
So how does the enable? Where do the enablers get connected? Do they connect with each other somewhere, or no, or yes?
The enable can come from an overall enable, or it can basically not really. They can just be um. Hold on, because I think there's a similar. He did a similar problem on one of the slides. Let me see if I can find it.
what exactly are they asking you to do for this problem?
To like describe it.
Describe the function of the two circuits below. Fill appropriate mixed logic signal names to clarify your description. Like, so what is it trying to tell you? That's just a 6 input mux.
Yeah, that's what I think it is. But it's definitely a 6 input mux. But I'm trying the enable.
I did the exact same thing as that problem for if you look at if you look at summer 2013 part D 9D. What I did was connect the enables and I did my truth table. I don't know if that's correct, but
Hold on. Yeah, I did that table too, and I got 0, 1, 0, 1, and I got the not. Yeah.
because what I did was I connected the enables, so one of them would always be turned off.
This was summer 2013, right?
Yeah.
On this, you just added the outputs together, right? From the top max and the bottom max.
Well, I did the SOP equation after I got all of that.
Yeah, but at like some at the beginning you added them together.
Look,
Let me see what your thing looks like. You got C naught A naught D B plus C G F naught D. Hold on, let me work out mine and then see if I get the same.
all right. Hey, when you have don't cares in a truth table and you're doing like the sum of products, you don't take them into consideration, that variable, if it's a don't care, right?
You can. You just have to make them either zeros or ones, so they give you the least. They give you a much shorter equation.
I can't find any examples of this Max's problems.
Hey, Ronaldo, let me ask you, is this correct? D, this one right here. What I did,
Um,
I connected the enables together, so automatically that turns off one of the muxes when the other one's true.
yeah. And then you connected that to C. Yeah, yeah, that's correct.
Yeah.
Yeah.
So, and I put don't whenever my other mux whenever my enable for my other mux is off, for the one that is off, I put don't cares for the inputs. Is that correct or not? They have to be zero.
Repeat that, please.
When one of my muxes is turned off because of the enable,
Uh-huh.
for my inputs I put don't cares. Is that correct or no?
Yeah, that's correct, because if not, you'll have to do a really big truth table.
Do I take those into consideration when I'm doing my equations for it?
No, not really. Can you show me once again your open collector question? I think I saw something I might have set wrong. Mike.
My open collector, yeah.
Um, yeah, so basically there's two configurations. There is a configuration in which you wire it and or. If you look at the slides, when you have when your output is active low, it's wired as an AND, right? And when your output is active low, it's wired as an OR. So basically, whatever two logics you have on your setups of inputs, it gets AND there or OR, depending on if the output is active high or active low. That's what matters, right?
Okay, so let's well, here they don't really specify anything, but I'm guessing if it's ORed it's low, and if it's multiplied it's high.
And it, yeah, basically. So all you need is just an AND gate, basically a NOT gate on your F, and you can put NOT first, and then on the other side will be F. You see what I'm saying? And then if it's OR, then it needs to be active high, I believe. Let me see, I just saw it. Let me make sure I'm telling you correctly.
Yeah, for the F, I made F active low and I put an open collector NAND gate. Is that correct?
Is he telling you to only use NAND gate?
He's telling me to use only open collector gates of any real SSI type gate.
Yeah, well, a NOT gate, it's a real gate, so you can just use a NOT gate if you want to. But
So
okay, so when the output is active high, it's wired as an AND, and when the output is active low, it's wired as an OR. So whatever two you have, whatever two equations you have, they're gonna be ANDed or depending on the output.
okay, so would this be correct?
Active low. Well, if you need F naught, then you need to have. Can you choose the activation levels?
Yeah, you could choose. I said it doesn't say anything about activation levels. The only one that's given to you is the O, which is active high.
So yeah, so then your F will need to be active low right there.
On the bottom it'll be active low, and on the top it'll be active high.
I think you want it the other way around because you need to have F naught, right?
Yeah, but if I have if I have F low for the top one, then I won't have to use any gates.
But if it's going into a mismatch, right? The thing is that you want to be F knotted, like F complemented. You see what I'm saying? Because that's what's on the equation. So if you have F active high on that gate that you're using, it's gonna stay it's gonna stay active high, right? It's gonna go active low on the other side. But that's not what it matters. It matters before, right?
Oh, you want it be like, no, I'm not really understanding too much.
So you want the equation is F naught, right? So how do you get F naught?
Well, you could use an inverter or just put it low, right?
Right. So which one are you gonna use? But the thing is, like, it doesn't matter on the other side, right? So it has to be knotted before it goes to the other side. You see what I'm
Before
saying?
before it passes that little line?
Mm-hmm. Right.
Yeah. Well, if I knot it before it passes that little line, that's why I used I believe it was a NOR. I used a NOR for active high, and it flipped it to an active low, a not high before.
Can you look at my screen?
Yeah, I'm looking at.
So basically, this is F, right? And
Yeah.
if you have it active high,
Okay.
right, and it goes through this, let's say you have just this, right? Let's say this is a hypothetical thing that I'm asking you, right?
Right.
So what will be the equation of this?
Those are not gates, right?
Yep.
It'll be F naught times B naught.
Well,
Wouldn't it be F naught equals B naught equals D?
uh, I don't. Well, this is a B. I don't have a D, so I just have. Yeah. So this will be on this side. It will be F naught, right?
Yep.
And here it will be not. So this will be the equation, right?
What is that on the right? Is that a D or an O or what?
It's an O. It's an O. So it will
Oh.
be O. Sorry. O high equals.
F naught equals B naught.
Right. So that will be the equation, right?
But you don't have an AND gate.
But they're tri-stated, right?
There's
So
one-
suppose this is like a resistor and this is VCC.
Every time the overall output needs to be high, you consider those an AND gate. If the output is to be low, you consider those as an OR gate.
Right. So
Oh.
this entire thing here is considered
As an AND gate.
it's considered a wired open
AND gate.
collector as an AND gate. So whatever you have on this side, it's ANDed. Like these two guys, these two people, whatever. If I add another term here, let's say if I add another C here, high, and then put it through just this and connect it to all of this, right? So what will be my new equation? What will that be?
It's the same thing. You just add a not C.
Well, I didn't put the bubble, right?
Oh, okay.
So this will be just C.
Yeah. Trick
So
So
question.
that's what you guys need to understand, that whatever logic happens behind here, it gets depending on this guy mainly, it gets ANDed or depending on this guy basically. So
Oh,
if
so
this
that
is
determines.
yeah, so if this is active low, so then we will have F naught plus B plus C.
so that what did you do right there to the C? You didn't. What is that? That's not an inverter. That's nothing, right?
Yeah, it's just a wire. So basically you can see it as just a wire with an open collector, so it's just you can do that, it's just nothing. So but basically yeah, Mike, your thing is correct.
It's right, right? I could do that like that, right?
Mhm.
All right. I could have just left it F low and put an open collector like that and not even inverted it, right?
Well, F low, the thing is you need the complement, right? So just F low is nothing. You see, F low, it's F low.
Yeah.
So you need the complement. So you need to put it through an inverter so you can complement that F, and then it'll be knotted on the other side.
I got a question about your original circuit, your original example that
Okay.
that said O equals F naught times B naught.
Okay.
If this was a physical real life wiring, if B is knotted and let's say F isn't knotted, it would just be F equals O or O equals F. You know, if it was just physical wires, because you got O going straight to F. It doesn't really matter what B is because there's still a wire connecting O to F, and vice versa. It doesn't matter what F is, you still have a wire connecting B to O. You know what I mean? So I don't know why they have to be ANDed because they're totally independent of each other. They can, you know, O is going to receive whatever B is, and it's going to receive whatever F is because they're just wires connected to O. You know what I mean?
I'm not following, but there is a connection here. Like all
Yeah,
of these
no.
wires are connected together, right?
Right. So if you're measuring with a voltmeter, if you're measuring at O, and
Okay.
you've got your positive on O and you got your ground on ground, right? If F, you know, you're gonna have it doesn't. What's weird is F and B, they just physically come together, and then if F is starts out positive, it becomes 0 volts, so then O is going to be 0 volts. If B starts out 0 volts, it gets switched to 3.3 volts, so then you've got 3.3 volts and 0 volts, which is just going to equal 3.3 volts. You know, it doesn't work like a traditional AND gate where both things have to be true in order to, you know, an AND gate would suggest that you have to have 3.3 volts and 3.3 volts in order to have an output of 3.3 volts, but that's not the case in this circuit. Either one of those inputs could have a 0 volts, and it wouldn't matter if the other one has 3.3 volts. You're still going to get 3.3 volts at your output. You see what I'm saying?
I see what you're saying, and I don't know specifically the explanation, but that's not the case.
But
The case is you're gonna get 0 volts.
yeah, if this was like a physical wiring, then and you're testing things with a voltmeter, you would, you know, if any one of those lines coming from B or the line coming from F were 3.3 volts, regardless of what the other one was, you would get 3.3 volts at O. You see what I'm saying? So it's not like it's not actually, it doesn't seem to actually be an AND situation. It seems to be an OR situation because as long as any of them are 3.3 volts, by the time they get to O, the output wire, then you're going to read 3.3 volts. Do you see what I mean? It doesn't matter what B is. It doesn't matter what B is or what F is, as long as one of them is giving you 3.3 volts by the time the voltage gets to O. You see what I mean?
I see what you're saying.
So it's hard to imagine that that's an AND situation, because an AND suggests both of them have to be 3.3 volts in order to output 3.3 volts. But that's definitely not what's happening in this wiring, because they're just wires connected together. And as long as anything is 3.3 volts, you're going to get 3.3 volts at your output. You see what I mean? So that's very unintuitive. It doesn't really make any sense if you go in like a physical, real-world wiring type of deal. So I don't know how they explain that. I don't know how that's explained, because it's really more like an OR situation. Because as long as anything, as long as B is giving you 3.3 volts or F is giving you 3.3 volts, you're going to get 3.3 volts at your output of O. You see what I mean? So I don't understand. Can you explain how that's an AND situation? Because if this is a physical, real-life wiring, it definitely doesn't work out that way. You know?
Mm-hmm.
Because if you just measured with a voltmeter, you know, you could start out with 0 volts for F. It gets inverted to 3.3 volts for F, which moves on to O, which makes O 3.3 volts. And it doesn't matter what the hell B is, because you've already got 3.3 volts that you need from F. So B could be the opposite. B could start out with 3.3 volts, get inverted, go to 0 volts, and then it's like, whatever, it doesn't matter. I've already got 3.3 volts at O. It's kind of I don't know if that creates a short circuit or what. It shouldn't, but it doesn't make much sense that that's an AND.
Yeah, but it depends where, because the VCC is going through the resistor first, man.
Yeah, I see that.
So would each of those be giving exactly the 3 volts, or wouldn't it be a combination?
Oh, it's because they're open collector gates. That's different. He didn't draw the little line coming off of the knots or something. Maybe there's a little different notation for that instead of just NOT gates.
That's the notation. If you look here, these are the lines.
Oh, I see.
I shared a PDF that I found a while ago, and it says that there are two cases with the open collectors: when the overall output is high or the overall output is low. And basically, when it's high, you treat them as an AND gate, so you just AND them together, and then when it's low, you just OR them together.
Yeah, we know that's a general rule. I was just trying to figure out why and how that works.
If you look at my screen, here's the explanation. So basically, there are transistors, right?
Oh, that's why. That's
You see
why
it?
they're actually transistors. They're not just NOT gates or anything.
Yeah. Every gate is just made out of a combination of transistors. So
That's totally different. That's why. I was just looking at them like they were NOT gates. I didn't know why you had that wire on there, but now it makes a lot more sense because they're not actually NOT gates. They're transistors.
Let me ask you. Let me ask you, Ronaldo, when you have an output that's active low, do you have to put a bar on top of the whole equation? Do you have to put a bar on top of the whole equation if you don't have a bubble there, or that doesn't take into consideration when you're working with open collector gates?
Yeah, that doesn't take into consideration. The only thing that it means is just everything that's going into that equation is just being or instead of and. So it's where as an and. I'm sorry, as an or, right?
Yeah. Okay. Yeah. Yeah. I just wanted to know that. I could do this Boolean algebra with this right here, right?
Um, so the thing is, right there, you're not in F, right?
Yeah, yeah. And what I did the Boolean algebra with not U plus O. I multiplied it and put the not O and then a bar on top of the whole equation.
Well, right there you have O is active high, right? And it's going into a bubble.
Mm-hmm.
So
Yeah.
that's going to be not it, right? So what right there what you're getting is not O and U. What problem is that?
That's problem 5, fall 2013 part B. What I was trying to do is not use as many gates. That's why. So I wouldn't have to use another inverter for U.
But it doesn't work out. It works out with O with a bar over it in the way you've got it drawn.
It works out that way.
Yeah, if you look, O gets flipped and it's got a bar over it now. We're going by the circuit diagram that you made.
Yeah, yeah.
So that's
Give me one
like
second.
a
Let me.
lower setting.
Yeah, so what I did, I used De Morgan's and I multiplied it. I put the not on top of O and a not on top of the whole thing. So it's so
Did he
it's
want you to simplify it like that?
no, no, no. He didn't want me. What I was doing that so I could just use one gate instead of having to use an inverter on U and then another AND gate.
Hmm.
Hey Mike, can you show what you did for those number 5 for part A and B? So you have a NAND gate there, and then your F high go there, yeah, and you have a G low, and then you have again. Is that at part B? Is that an AND gate or an OR gate?
For what? For the OU?
Yeah, OU.
That's a Benand.
And O is high and U is low.
Yeah.
But why did you do it that way?
Because what I did was okay, you see, so right there I turned this into this.
I don't know if we're allowed to do that.
Yeah, that's what I wanted to ask him. But you know, I did that so I won't have to use two gates.
You did what?
I did the Morgans for O and U.
But why can't you use a simple OR gate there?
Yeah, just use an OR gate. You can't. The Morgans, it's
So the way I did it is um
Oh, you just used an OR gate?
yeah, the way I did, I'm writing on the screen right here that I'm sharing it. So it's like an O high, and then it goes through an OR gate, and this is an a U low, and then the bottom is an F.
That's actually G low, no?
No, it doesn't matter because the output here, you want the output to be a high, so it's like you have not a gate, you have not a bubble in here, and so the output is gonna be O plus uh, U bar.
No,
Is
I'm
that
talking.
right?
Your output isn't a G. It's not O.
He
Yeah,
hasn't
I
drawn the
know,
up.
but
Yeah, I know.
bottom.
He's not done with the circuit.
So the
Oh.
output is here, and it's a G high. And then also here you have an F, which goes through not an inverter, but goes just through an open collector without a bubble. And then also you have a resistor down here at the top. So I got an O high and a U low going through a regular OR gate, and then I get and then I get an F high going through an open collector. Is that right, Ronaldo?
Yeah. If you
So
look at my screen, that's the same thing I did. Well, G G has to be low because you want to OR them together, right? So,
I'm talking about part B.
oh, part B. Oh, my
Yeah,
bad.
part A. That's what I got for part A too. Yeah, for part A, that's right. You want your G to be low.
Yeah, I understood exactly what you did. It's much easier that way, just putting the OR
But
gate.
also on your screen, Ronaldo, you need your bars after the gates,
Yeah,
right?
yeah. You got regular NAND gates instead of the bar going through it.
Oh, yeah, that's right. Sorry, I forgot.
That's misleading.
Yeah, sorry, my bad.
Yeah. The one that I was talking right now was part B.
Um, yeah, that looks correct. It's O or with U naught and then F. Yeah, that's correct.
So
And they're ANDed.
F goes through a open collector but without a bubble, right?
Yep.
Yeah.
Yeah, that's a lot easier. I don't know why the hell I decided to switch that to.
Well, you must not have thought of making a U active low, because that makes it so you don't have that weird situation.
Yeah, yeah. I don't understand why I even complicated my life.
It says that's all. Yeah, she's gonna be
No
parking
more.
down where you at. For sure, she's gonna be parking down there. Yeah.
Which
Oh,
test is this that you guys are doing?
That's fall 2013.
Oh,
Hey Reynaldo, did you ever come across that problem? The enables in the problem are through tri-state. So the 6 input mux, like what exactly were you supposed to do with that one?
Yeah,
No,
number
I'm not sure, honestly.
we're talking about that, but yeah.
there's more of these problems on summer 2012.
All right.
You guys want practice on those, man, on the open collectors.
Is an open collector really just another name for a transistor, or are they kind of different?
It's just all the gates are made of transistors, right? So even your NOT gate and your AND gates and stuff. The thing with the open collectors is the way you connect the wires and you put the resistor to VCC.
Oh.
They're always pull up high, right? So you can actually connect them together. See what I'm saying?
Yeah.
Hey Ronaldo,
Mm-hmm.
can we work out problem 10 on the fall 2013? I'm putting it on my screen.
Okay.
Hold on, I'll share my screen and I'll try to work it out and yeah. So it says there is a priority encoder, and also so we need to create a
Truth table.
truth table. So I made x0, x1, 2, and 3, and this is y0 and y1. So y0 and y1 basically go 0, 0, 1, 1, 0, 1, 0, 1. Now when it's 0, 0, it's supposed to go 0, 0, 0, 0, right? But when it's 1, it's supposed to be x, 1, 0, 0, right?
Yes.
Yeah.
Yes.
And then when it's when it's 2, it's like it's 1, 0, and those are x, so these are x, 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 and this is 1. So that's the truth table.
Mm-hmm.
And now it says create a functional block diagram. So here we're gonna have to label these things like A1, A2, and A3.
How come x0 wouldn't be 1 in your first row?
I think Y0 has to
Oh, yeah.
be 1.
Yeah, x1, x0 needs to be 1 on the first row, yeah.
Yeah.
Yeah, I forgot about that. So, and this, you just label them as like A0 through A3 or whatever.
Mm-hmm.
And you just put your activation levels. That's all you do there.
Mm-hmm.
All right. And then here, determine the equation for the encoders. Design a circuit, and to determine the equation, how do we determine the equation of y0 from the? Do we use K maps here, or like how can we do this?
Well, you can either use K-maps or you can more easily just use the main terms, right? The sum of products and the products of sum. The main terms and the max terms.
All right.
If we were going to use a K-map, would you'd have a K-map for y0 and a K-map for y1, and then your inputs would be x0, x1, and then x2, x3. Is that how the K-map would look?
Mm-hmm.
So if you didn't remember the shortcut for these, you would just do K-maps for Y0 and Y1, and you'd get it that way too.
Yep, exactly.
Right, let me do the K-maps real quick. So we need two equations for this, right?
Right.
Yeah, Y0 and Y1.
Okay, I'm doing those right now and see what equations am I gonna get.
No, it probably follows some kind of pattern, but I don't know what the pattern is.
Could I see really quick what you put on your truth table to see if mine's is the same?
Can you see it?
If you could scroll it, okay, let me, yeah. I
How
got,
come those are zeros? Wouldn't those also be don't cares for like it'd be one don't care, don't care, don't care for like the first row?
No, no, I think
No, because
zeros, I think.
yeah, because if you have a 1 and a 3,
Oh yeah,
then
yeah, because those have higher priority.
mhm.
That's why I forgot.
Remember on your functional diagram to also label your outputs, so RFS. I don't know if you just didn't do it or did.
The outputs. But on this functional diagram, the x1 here has a bubble, which means that a2 should be a low, right?
Yeah, that also.
And then y0, if I name my output z, it has to be a low, right?
Mm-hmm.
So z0 and then z1, it has to be a high.
Mm-hmm.
Alright. For the equation, I got y naught to be x2 plus x3. I don't know how, but it doesn't sound that right, but
Can you share with us somehow? How do you get it?
well, I filled a K-map and hold on, I'm opening another Excel. Um,
you picked all your activation levels to be high?
um,
It depends on the chart. Some of the ones with bubbles are active low, and the other ones are active high.
it doesn't matter at this point, I think, because it's we're not concerning with voltage, we're just concerning with the logic.
Yeah, it's probably going to matter later on.
Yeah, later on when we draw the thing, when we draw the, I started an Excel now, so I have x2, x3 here, and x0, x1, and then here. So at x0, when x0 is 0, 0. Oh, come on. How do you format the data here?
I don't know.
I remember doing it once, but
Just type
If
0.0 and see what happens.
you go to home, and
oh
is there
yeah,
where it says general?
yeah, you make it text. What the hell happened? So, and this is for y0. So when x0 is 1, and this is gonna be 0 when x1 is 1, and doesn't matter what what's in front of it, but the rest of them are 0. This is 0 and this is 0. But when x2 is 1, which is right here, and doesn't really care about what's in front of it, yeah.
I have a question for priority encoders. Is the higher number generally the highest priority when
Yeah,
they're
unless
written
otherwise
out?
specified.
So you can just generally assume that the highest number of the input is the highest priority.
Mm-hmm.
All right.
And then so that's what I got.
And it resulted in two big circles, right?
Well, it results in only one circle here.
Oh, of zeros. Yeah.
Or on one here and one here. Yeah, either way will work.
Yeah, but the fewest amount of circles is just zeros down the first column.
Yeah, and then for y1, I was getting 0 here, 1 here, and 1 here. And then when x2 is 1, which is here and here. One zero, which is right here, was 0, 0, 0, 0. So for this one, I get this here and this here, and also
It crashed.
no, it didn't crash. So there is yellow and this red numbers,
Okay.
and the equation for that is
Why you have so many ones? Where are you getting those ones from?
because based on the table that we filled out, right? So we filled out this table, which was x. Well, let's start x3, x2, x1, x0, and then we have y1 and y0, right?
Mm-hmm.
So this y goes 0, 0, 1, 1, and the counting here goes 0, 1, 0, 1, right?
Okay. But okay.
And then when this is 0, 0, these things are all 0, 0, 0, but x0 is 1, right?
Okay.
And then when the value here is 1, these are 0, 0, this is 1, and this is don't care.
Mm-hmm.
And this is 0, this is 1, and this is don't care, and this is don't care. And
Mm-hmm.
when the value is 3, this is 1, this is don't care, this is don't care, this is don't care.
Okay.
But do you understand me so far? Is that
Right.
what needs to be done? So now to fill out the K maps we have for y0, we see where x0 is 1, x0 is 1 here,
Yeah, 1000.
Mm-hmm.
1 0 0 0, so we fill this table to be 0 from here.
Mm-hmm. Okay.
Alright? And then we
Right.
go down to the next one, we see x1 is 1 0 0, which is right here, 1 0 0, or 1 here, because it doesn't care what's in front of it, but it cares what's out of, after it. So here and here, these are zeros.
Okay.
And then we go again at x2, which is at don't care 1 0 0. So 1 x2 is it's 1 0 right here, right? The whole this column. It doesn't care what's in front of it, so we make this all with ones.
You should have written them as X's though, because you've already decided they're ones and you wrote them as ones. But normally you just write them as X's and then decide they're ones when you do the K map.
No,
No,
but you can't do that because they have to be ones.
no, there are ones. They're not don't cares.
Yeah, they have to be ones because the don't cares is on the variable side, not on the output side. Do you see it,
Um,
Tony?
yeah,
His name is not Don.
no,
Well, I'm going by what I see.
yeah.
uh, um, and
Tony's
then
smart.
x3 is 1, and then it doesn't care what's after it, so it's like x3 is here 1 and it's here 1, so all these things here are gonna be 1, so that's how I got all those ones.
Okay, that makes sense.
And now we do the same thing for x1, and we found this table, and we have two product of sums. So it's gonna be x2 not plus x3.
I think you made a mistake on your K map when x0 is 1. No, that's right. That's right.
So I got the equation for y naught to be x2 naught x2 naught plus x3 times x3 plus x1.
Can you write it down in Excel?
Yeah.
Yeah, look, on y0, when x2 is 1, y0 is all zeros.
Can you say that one more time?
When on y0, when x2 is 1, it's y0 is all zeros.
When x2 is 1, so x2 is 1 here, and x3 is 0. Yeah, but you gotta look, x2 is 1 and x3 is 0, which is right here, right?
Yeah.
And
So it should be zeros because you don't care about x1 or x0.
yeah, you're right. I don't know why that was 1.
Yep.
No, that's right.
It should be zeros.
It should be 0 based on this table, but based on the previous table, it should be 1s. But
Oh. Yeah, it's confusing because you wrote your table one direction and you wrote your K-map the other direction.
yeah, I wrote the table other way, and I wrote this. It's
Yeah.
like all messed up now.
It makes it hard to follow.
Guys, I think what we can get out of this is that this is taking you a long time and it's very prone to errors.
Oh yeah, there's a shortcut.
So I will go with the main terms and the max terms.
Okay, can you show us that? Is that a process or is that something you just know?
It's just like the vectors. Like if you go back, let me pull up the slide. So for instance, if you see his truth table, right? So you got y0, right? Or y1, whatever, whichever. Let's start with y1. It's so you pick which one you want to do, the main terms or the max term. So for instance, here it doesn't matter because you have the same numbers of zeros and ones. So it doesn't really matter. So I'm gonna go with the ones, right?
Okay.
So then it will be just so when you're doing the ones is a sum of products, right? So you have x3 plus x3 naught times x2 plus x3 basically.
Okay.
For what? For which one is that one?
For y1.
You take into consideration the don't cares?
No.
So you'll have only x3 plus x2, no? For the sum of products?
No, x3 times x3 naught times x2 plus x3.
But well, you're getting that from the truth table, right?
Right, so if you look at the third row where you have y1, you have 0, 0, and then it's a 1, right? So you look to your left, and you basically, you're gonna have a term there, right? So whenever you have a 0, that's not it. So you have x3 naught,
Yeah.
and you're doing a sum of products because you're looking at the ones.
Yeah, times x2.
Times x2. So that's it for that term because the other ones are don't cares, right?
Plus x3, right?
Plus x3. That's it. That's your y1.
All right, yeah. And so then y0 is just x3 plus x1, unknotted with the other ones, right?
Mm-hmm.
So this is just x3 plus.
So what were the equations one more time?
x3 naught times x2 plus x3 for y1
x3 naught times x2
plus x3.
that's for y1, right?
Mm-hmm.
And what about y0?
So for y0 is x3 plus x3 naught times x3 2 times x1.
So it's x3 plus x3 naught times x2 times x1.
Well, the x2 is knotted.
All right, but okay.
That's for y0.
Okay, so x3 x plus x3 naught times x2 naught times x1.
Yeah.
And then y1 was x3 naught times x2 plus x3.
Yeah.
All right. Okay, so you get these equations, and then in the test it says design the circuit. I think we can do that. And then on part C it says which of the outputs Z are true for each of the following. So like, how do we do it here now?
Well, that you could do without anything. You can just realize that 3 is the highest part, you look at the priority of it, and like for number 1, it says x0 is 1, so they got them connected in a weird way.
Yeah, but so you'll look for number 1 and you see that it's x0, so x0 will go through, and then
Yeah.
what's happened then? Which one of those goes? Goes y0 or y1?
I don't know.
You tell me. So when you have um
It's like
Yeah.
y is the
When
input.
when x0 is going through, it's supposed to be 0 0, but since y0, it's supposed to be y0 0 and y1 0, but since y0 is an active low,
But it's
it's
that's the one.
connected to an active low, so it doesn't
It should
matter.
be z0, right? Should be the answer.
Well, you have to give an answer for all the outputs. Oh no, only which one is true?
I guess. Yeah, isn't z0 what happens in that first situation?
Okay, guys, this is this is very easy. So think exactly about what's happening. You have a priority encoder, and
Yeah.
then you're decoding it. So think about that. What is it that you're always gonna get?
The input.
The binary
Exactly.
number.
Exactly. Whatever you put into it, you're encoding it and then you're decoding it. So whatever you put into it, you're gonna get exactly the same thing
Right.
outside.
So aren't I correct in saying z0 is the output?
Yep.
All right. And the next one, I don't know what it does because it selects nothing. Well, it should just select z0 again, I guess.
Yeah, I guess that depends on. I guess that's a good question to ask. What does he want when it's 0 0, or maybe no output is selected?
Yeah.
Like you get 0 0 0. So yeah, you will. I think you'll definitely get the same thing.
And then the number 3 is z3, and then number 4 is going to be z3 again.
Yeah.
Mhm.
Yeah, because the other ones you don't take priority of the other ones, right?
Yeah, they don't matter. Okay.
All right. Well, thank you, Ronaldo.
Yeah, appreciate it.
All right. Anything else? I mean, I don't mind staying a couple extra minutes. Any other question you guys have?
No.
No. Besides those encoders, besides those muxes with tri-states, I think we're good. I'm just gonna email Schwartz about it.
Okay. All right. If you guys want, I can do it, or you guys want to take care of it.
You can do it.
I mean, you can do it, but you said that you were not sure about it, so I don't know.
Yeah, I'm just gonna tell him to explain, and then I can explain to you guys.
Oh, so like you're gonna get the backup later?
Yeah, I'm gonna get back to you guys later. I'm gonna try to write an email explaining it.
Alright, yeah. If you want to do that later this weekend, you can, if you have time.
Yep. All right.
Alright.
Anything else?
Hey, Renato,
Yep.
that's it. You have no more office hours, right?
Not until Monday morning.
Monday morning. And You're located where? Here in Gainesville now or no?
No, I'm not here. I'm not there. I'm in Fort Lauderdale.
Well, you won't tutor over this?
All right, let's do something. Um, I'm gonna get the answer, and you two guys are interested, right? You, Irvis, and Mike.
Yeah.
David.
Okay, so the three of you guys, please send me an email so we can maybe set up a meeting time during the weekend, and we can go over this. Or yeah, maybe I can even do it like for everybody, so it doesn't matter. So what time is good for you guys?
Um,
I'm whenever. I don't. This weekend I took off of work. I'm go whenever.
Yeah, same here.
8 in the morning.
So let's say um
for me, it would be good sometime after 3 o'clock, 3:30.
on Saturday.
Yeah, Saturday. That's fine.
Okay, so let's say Saturday at 4 p.m.
All right.
All right, so on Saturday at 4 p.m. I'm gonna do an extra hour, and I'm gonna get back at you guys with the Max problem. Okay?
Okay. And you're gonna send again the link for the Hangout, right?
Yeah, I'm gonna send it again to everybody, so just watch
Alright,
out for that email.
All
that's
right.
cool.
Okay. Appreciate it, Ronaldo.
All right, no problem. Thank you, guys.
Reinaldo,
Yep.
te voy a mandar un email ahí con una pregunta rápido, man.
Go for it, man. Go for it. Oh,
No tiene que ver con esto,
okay.
¿ok?
Okay.
Dale.
All right, no problem. See you guys.
Yeah.
Take it